In this chapter, we will learn about the basic physics of semiconductors. Now the question is, what is semiconductors? So we know that the concept of conductors and insulators. Conductor, it can conduct the current, for example, copper or silver or gold. For insulator, it stops the current flow. It cannot conduct any current. So, for example, glass, right? Or the rubber or whatever. But the semiconductor is somewhere in between conductor and insulator. What does it mean? It can sometimes conduct or it cannot. So the typical characteristic of the conductor has the like this. So for example, if the temperature rises, for example, the conductivity go up or down. It goes down. Why? Because if you add more temperature, increase the temperature, the lattice structure will vibrate. So the electron passing through the lattice structure will be somehow hindered. So it is somehow the the movement of the electron will be somehow the affected. So the movement of electron is not good at that point. But in semiconductor, as the temperature rises, surprisingly, the conductivity goes up. What is happening inside? Let's take a look at what is the semiconductor. Semiconductor composed, for example, there are two different types. One is a single element semiconductors. One is the group 4 material like a silicon and germanium. For example, here, right? Group 4 material. The silicon is abundant. Like if you go out the sea, then lots of the sand there, so we can purify the rock or sand to get the silicon out of it. So it is very cheap, so we can get that silicon easily. Another one is the compound semiconductors. The compound means it made out of more than one element. For example, here group 3 and 5, here 3 and 5 elements they used to get the compound, the semiconductor. For example, gallium arsenide here, gallium arsenide can form a semiconductor. So now the question still arises, why the temperature goes up and conductivity goes up. Let's take a look at that in the next slide. This is the two-dimensional representation of the silicon material. So the silicon, since it has the 4 electron, the outermost the shell, so let's represent that just this line. We have a 4 electron at the outermost shell, and then this silicon structure, silicon atom, form a lattice structure like this. So it share the electron. So the total at the outer shell, we have a total 8 electrons in there by sharing the electron from the nearby silicon atom. So it forms like this solid the structure like this. So there's no mobile carrier, so no electron, free electron there. But if you increase the temperature, so the lattice structure somehow get the energy from the temperature rise. So this kind of thermal energy actually break this kind of bond. This bond is called the covalent bond, because it shares the electron at the outermost shell. So it is called covalent bonds. So thermal energy actually breaks this covalent bonds and release the free electron like this. And then if the electron is the release like this, we can think of the other way. There's a void connection, like there is a missing electron there. That can be think of as the hole, right? So free electron and hole are kind of generated. So if this kind of, for example, this here, the electron moves around the current flows, or the hole in the other way, if the hole location moves from left to the right, this kind of a thing forms the current flow. Okay, and this kind of a hole and the electron pair generation happen as we increase temperature. And it frequently hole and electron generation happen, and also at the same time the generation and the recombination of the hole and electron pair happen at the same time, right? So this kind of a thermal energy actually increase the free electron and holes. Those can be a carrier for the current. Okay. So inside the silicon lattice, a hole and electrons are generated as a pair. So the number of the free electrons and holes per unit volume will be the same. So let's say that the number of electrons per unit volume, in this case, centimeter cube. This is 1 centimeter, 1 centimeter, 1 centimeter cube, right? So it's 1 centimeter and 1 centimeter. In this volume, we can count the number of a carrier. Let's say that is N for the electron and P for the hole. So this number, the number of a free electron and hole inside the silicon is the same, so we call it like Ni. So this is called intrinsic carrier density. Okay, this intrinsic carrier density, so if the temperature rise, then Ni will go up, right, as I explained before, right? So hole and electron, the number of hole and electrons are increasing, right, as we increase the temperature. So the scientists found out the actual number and the carrier number versus the temperature. We have this relationship, right? We have a temperature to the power of 3/2 and exponential, right, here 2 kT. So K is Boltzmann constant and T is the temperature. The Eg is called the band gap energy. So this is different for different material. For silicon, that is 1.12 electron volt, and for diamond is 2 electron volt, right? This is the energy. So for example, in silicon, the energy level, band gap energy level is so we can calculate the electron volt to the joule. So electron volt is the amount of a charge there. We can find in the amount of charge times 1.12 volt and give us the 1.792 times 10 to the power of minus 19 joule. So if we plug that number into the above equation, for example, N sub I with the temperature around 300 K, that is typically room temperature around 27 degrees C. So we get this number 1.08 times 10 to the power of 10 electrons. And for the temperature 600 Kelvin, we get the 1.54 times 10 to the power of 15 electrons per cubic centimeter. Now this number seems like a large number, but this is not a big number for the current flow. So this is a very poor conductor. So we need, if you wanna use the silicon for good conductor, we need to do something else. With the current silicon, pure silicon, we cannot get the good conductivity out of this. Okay, we will see how many electrons should be there for the good conductivity. Okay, for now we just have to understand this number is not large. Okay. Now the question is how to make silicon look more like a conductor. So there should be more free electrons. Now the thing is that we can do, we add impurities like so currently silicon has the 4 electron at the outmost shell. What if we add some material from the group 5, which has 5 electron at outmost shell? So for example, phosphorus here, we have a 5 electron at the outmost shell. So 4 electrons are shared with the silicon to form the lattice structure, and then 1 remaining electron is there. So this electron is not attached to any atom. So this 5th electron actually unattached to other atoms. So this increased the conductivity. Okay, so this kind of an action of adding impurities into intrinsic semiconductor is called doping. Okay. So the impurity, for example, phosphorus in this case, is called dopant, right? So we added the dopant from the group 5, right? Here in this case, to get more free electron. Okay. So this is called N-type silicon. From the pure intrinsic silicon, the carrier type is electron. So this is called N-type silicon. So we add the group 5 material. Okay. Now, if you wanna have if you want to add more holes if you want to generate more holes, then you will add material from group 3 instead of a group 5. So the outmost shell, we have the 3 electrons. So one void connection creates the hole. Okay, so that is called now the p-type silicon. So far we just looked at the n-type silicon. Okay, so as we have shown here, so we add group 3 material like a boron here that will create one void connection. There's no missing connection there, so that will actually create the hole. So this hole can contribute any current flow. So if you remember, the actual movement of a current is done by electrons. So how come this hole can contribute the current flow? Some student may ask. But this action is that if there's any free electron nearby, it will be trapped by that hole. So this trapping and releasing will actually contribute the movement of an electron. So we can think of this current flow instead of electron movement, we can think of that as the whole movement, right? But physically inside, the actual behavior is electron, right? But in this case, since there are lots of a hole, so it is easier for us to understand or visualize the movement of the current flow by showing the whole movement. Okay. Now there is important relationship arise like this. So in both intrinsic and extrinsic, right, semiconductor follows the following. So this satisfies in both cases number of electron per unit volume and number of hole per unit volume is always equal to intrinsic carrier number square. Okay, why is this happening? Why this relationship holds true? We will see why in the next slide. So this is a very important relationship and very handy, right? I visualize the basket. The one basket holds the electron, the other one holds free holes. So in intrinsic semiconductor, we have the same number of electron and hole, right? Let's say we have the same electron and hole, right? About the same amount, right? This much, for example. So the in intrinsic semiconductor, so N equal P equal Ni, so NP times is Ni square, right? We know that. Now we add impurity, so large group 5 of material, lots of electron, free electron here, right? Pouring into the intrinsic semiconductor, for example, silicone like this, right? If you pour that, if you add this kind of this much impurity, right? For example, now after add the impurity, now the electron number of free electron would be what? How much? What will be? How many there? So you may think of the Nd plus Ni, right? But you can think of the other way, because if you have a lot of electron in there, so the number of hole here, so the many empty space that can be easily filled by abundant electron. So almost there's no free free holes there. So most of the hole and electrons are recombined, right? So lots of recombination happen. So the number of electron would be about the same as the dopant. So Nd, right? Like this. Now the number of a free hole now in turn, so the amount, so that will not be completely zero. We get the more electron there, so it has a higher chance of being recombined. So the remaining number of free hole would be the decrease by Ni over Nd. Previously we had the Ni of the electron, but now the Nd of the electron. So we have some higher probability that for the electron free hole can alive. So number of hole would be what? From the Ni to Ni times right? Ni times Ni over Nd. So the number of electron, number of hole would be Ni square over Nd, right? Approximately, right? So now if you look at this relationship there, the free electron, number of free electron is Nd, but the free hole will be Ni square over Nd. So if you multiply those two numbers, that is also similar to close to Ni square. So number of free electron given by the Nd, and number of hole, those that will be same as Ni square, right? So this happen also in this relationship n times p equal Ni also holds so in extrinsic semiconductor. Also holds true, right? Right. So the starting from intrinsic semiconductor in this example silicon, we can this is intrinsic semiconductor can be either n-type semiconductor or p-type semiconductor, depending on the types of dopant. So here the group 5 material as the additional free electron. Here group 3 material generates the hole there. So in both cases, for example, for n-type device, so the dopant is the electron, so n equal to Nd. So dopant density. So and also on the right hand side, p-type semiconductor, the this is called the acceptor. So this like the donor. The n-type is donor because this is electron. This is like a donor, and for the p-type is like an acceptor because it's the empty space which it can be easily filled by the electron, right? So it accepts the electron, right? So this kind of the number of donor in cubic in the unit volume is Nd here. So for the number of acceptor in p-type is Na here. So N is electron density and small p is the hole density. So in both types of the extrinsic semiconductor, we have the same equation n number of electron density times number of hole density is always equal to Ni square, right? Ni square. And also on the right hand side it's also Ni square, right? So easy or handy to manipulate with this relationship. So, right? So intrinsic from the intrinsic and the extrinsic. All holds the same, right? So based on the np times Ni square, we can know that if we know one of those two electron or hole density, we can find the other the types of carrier density. For example, in n-type semiconductor, if we know that Nd number of electron density, so electron density is known as Nd, then the hole density can be easily found. That is Ni square over Nd. So majority carrier in n-type is electron, so electron density is N, and that is Nd. So in minority carrier in n-type is hole, so hole density can be Ni square over Nd, right? So if we know the So if we control the ND, then we know that we can control the minority carrier. That also holds for the p-type. If we know the Na acceptor, like a hole density, then we know that electron density. Electron is a minority carrier in p-type, right? So one is given, then the other carrier density can be easily found based on this kind of a equation. Okay. This is some simple the exercise. Let's assume that let's read this the question. A piece of a crystalline silicone is doped uniformly with the phosphorus atom. The phosphorus is the P that is from the group 5 material, right? Group 5 material. The doping density is 10 to the power of 16 atoms per cubic centimeter. Now, determine the electron and hole density in this material. Because the doping density is 10 to the power of 16 atom, we know that electron density is same as 10 to the power of 16 electrons per cubic centimeter. Okay. Now at room temperature Ni, the intrinsic carrier density is 1.08 times 10 to the power of 10, right? Now the minority carrier hole density can be easily found by Ni square over N, right? So doping density is given by the 10 to the power of 16 atoms per cubic centimeter. We can find the minority carrier. In this case, hole density, like this. Okay. This is just a simple math. Okay. It's not complicated at this moment.